All right. Today we're gonna, you know what? First, let's look at the homework that's due next Monday because I think it's gonna be hard. That's why I made it 20 points. This might be the last homework. I'm thinking about maybe doing one more, but it might be the last one. Okay. So this first one I think you could do right now, but I think it will take you some time. So I said two sinusoidal waveforms are plotted below. Both waveforms have the same frequency, but their amplitudes are different and they're not in phase. Is that obvious to everyone?
No.
Hopefully it is. Is it? Not? If it's not, we can talk about it.
It's obvious they're not in phase, and their amplitudes are different.
Yeah, that's it. I'm just asking if that's obvious.
Yes.
Okay. So I'm asking you to determine the equations for V1 and V2 as a function of time. And I gave those standard forms, right? It's the amplitude times the cosine 2 pi ft plus the phase. So, and I'm telling you that V1 is a phase of 0, okay? So that's just a cosine. So you're basically referencing your phase to that blue signal. I ask which signal's leading, which one's lagging, and then I tell you to verify that your equations are correct by regenerating this plot. But I said run for 15 milliseconds instead because I don't want you just snipping this and saying you regenerated it. And if I said 10 milliseconds, you still could have done that. So you have to run for 15 milliseconds. And then I said finally determine the phasor representation of V1 and V2. That you might not be able to do yet because I haven't done a whole lot with phasors, but today we will. And then last time I started getting into how to solve these AC circuits with phasors and impedance and whatnot. Today we'll go further into that. But you should be equipped to solve, or at least start trying to solve this by the time you leave here today.
Is this the last homework?
It may be. I might do one more after this.
Okay.
I'm still trying to decide, depending on what I cover, how much I get through today and what I cover next week. Okay, so let's get started.
Are we going to learn how to set phaser to kill?
No, not here. Let's see if this is going to act up. Yeah, that's exactly what I'm going for.
Killing robots.
All right, so
Because the robot won't let you.
So I'll just start with a brief. Give me like 10 minutes to review complex numbers, because this will be very useful. There will be no quiz, so we're going to go for the whole time today. Complex numbers have a real part and they have an imaginary part. Okay, everybody remember that? Maybe you don't remember this. Typically, they're written in the form of x plus, I'm going to use j because that's what we use in engineering. Again, I wrote it up on the whiteboard. J is just root -1, right? That's your I. That's I in complex numbers, but we use j in engineering, okay? So complex numbers are written in this form, x plus jy, where x is the real part and y is called the imaginary part. All right? And so when you have a complex number, you can plot these numbers in the complex plane. And maybe you do or don't remember the complex plane. The complex plane is basically where the x-axis is the real and the y-axis is the imaginary. Okay? And so let's say I wanted to plot some imaginary number. I'm going to say z equals 2 plus j3. Okay? So I want to plot that number. So what I basically need is some ticks. So if I go 2 in the real direction, right? 2 in the real direction, 3 in the imaginary direction, I get this point here, right? Where this would be z equals 2 plus j3. Everybody cool with that? All right. Now, if I draw this as a vector, which it basically is, that vector has a length. And that length is really, really easy to calculate because we can just use Pythagorean's theorem and determine the hypotenuse of a triangle with basically, let me just draw it. everyone would agree that this side of the triangle right here has a length of 2, and this side of the triangle has a length of 3. Okay? We know that a squared plus b squared equals c squared. Okay? So basically what I'm trying to find is the magnitude of this. I'll call it magnitude of z. Those two like vertical lines mean magnitude. Okay? So you're going to get used to seeing that. Okay? So if I want to write this, I could say, you know, the magnitude of z squared is equal to 2 squared plus 3 squared, right? This is just Pythagorean's theorem. Okay, so if I want to find the magnitude of z, I square root both sides. And I get that the magnitude of z is equal to the square root of 2 squared plus 3 squared, which in this case is root 13. Right? 4 plus 9. Okay, so that would be my magnitude. My magnitude, or basically the length of that vector. This is just complex numbers with no application yet in engineering or AC circuits, but this is going to be very important because it's going to be the exact same. This is what we're doing when we solve these AC circuits. It's just not explained this way anywhere, not in the textbooks. I've never seen it explained this way, but this is what's happening. It's just the basic complex numbers, and you're finding the length of that vector. Okay. Because I don't know if you remember last time, but when I talked about phasors, I said that the phasor has a magnitude and has a phase. This is the magnitude right here. That's all it is. So when we get these things in terms of complex numbers, when I say find the magnitude of that signal, this is the same process that you're going to follow. Okay. So that's the magnitude, and now let's look at the phase. The phase is basically the angle from the x-axis. Okay, so this angle right here. So I'll write it as phi. Okay. Everybody can see that? So that angle right there, if you remember, how many of you guys heard of SOHCAHTOA in geometry? Okay, so if you haven't heard of SOHCAHTOA, it's written like this, where it basically means the sine of an angle is equal to the opposite side over the hypotenuse, the cosine of an angle is equal to the adjacent side over the hypotenuse, and the tangent of an angle is equal to the opposite over the adjacent. Everyone's familiar with this, probably? If not, that's kind of scary. Okay, so we're going to use the TOA part because to find this angle, we have the opposite side and we have the adjacent. Okay, so if I say the tangent of phi is equal to the opposite, which is basically 3, over the adjacent, which is 2, I can find phi, that angle, by taking the tan inverse of both sides. Okay, so tan inverse of the tan of phi is equal to the tan inverse of 3 over 2. And then the tan inverse and the tan basically cancel each other out, and I get that phi is equal to the tan inverse of 3/2. Okay? So now I just found my phase, and I found my magnitude. That's my phasor right there. That's literally all a phasor is. We're going to plot this complex number, and we're going to represent it in terms of its magnitude and its angle from the x-axis. Okay? So this, you would write it basically, let's see, what's the tan inverse of 3/2? 56 degrees, 56.3. So it'd be z, this complex number, which was 2 plus j3 in the imaginary, or the complex domain is what we'd call it. Or also called rectangular, okay? In polar form, how many guys remember polar coordinates? This is the same stuff. It's just the magnitude is your radius and the angle is your phase. It's the same thing. So you're going to call this typically rectangular. The reason you need to know this is because your calculator will call it this. So this form is called rectangular form, and this form is called, well, not polar. Polar, okay? So this form, all I'm going to write is my magnitude, angle, phase. So it will be root 13 angle, and I calculated 56.3. Okay? So it's perfectly okay and correct to say that z is equal to 2 plus j3, and it's also perfectly correct to say that z is equal to root 13 angle 56.3. Those two things are equivalent, but this is in rectangular and this is in polar. Okay? Any questions before I move forward? Because this is the gist of pretty much everything that we're doing from here on. In 221, the first several lectures will be this stuff and applying it to circuits. Everybody good with this? Question?
So why are we doing this? Like why are we changing from rectangular to polar? Just so that we can get the angle and the magnitude of the focus?
Yeah, it's because basically, like I just showed in the homework, what we care about in these signals is getting them down to a form that we can analyze them. Okay? A lot of times, so basically the way that the textbook will describe it to you, and it's true, is that we basically have complex signals here because we have impedances that part of the impedance is dependent on frequency and part of the impedance is not dependent on frequency. Okay? So this is not happening in real life. There's not like some imaginary component. They're just using this same mathematical structure to make analysis easier. Because when you get an impedance, right, if I have 2 plus J3 and I call this an impedance, that means that my impedance that's not frequency dependent is an impedance of 2, and my impedance that is frequency dependent is an impedance of 3. So it's just using this same mathematical structure to basically keep everything organized when we analyze these circuits. And it's really, really easy to add and subtract two complex numbers, okay? If I have, let's say, let me get a different color. If I have, say, 2 plus J3, and I want to add that to 4 plus J1, typically that would just be written as J, just so you know. I wouldn't write J1 normally, but all I do is add the real parts and I add the complex parts and I get the sum. So this would be 6 plus J4, and that would be completely correct. Okay? Subtraction is just the same. However, multiplication and division is not so easy. You have to factor, and it's kind of a pain. But multiplying phasors is really, really, really easy. So they typically ask you to, and dividing them too. They typically ask you to do some addition and some subtraction when you're trying to do KVL, and do some, multiplication and division when you're trying to do KVL. So what you'll do is you'll do the addition and subtraction in this form, and you'll do the multiplication and the division in this form. Because to divide or multiply two phasors, all you do is divide or multiply their magnitudes and add or subtract their phases. So it's a lot easier to do addition or multiplication and division in this form. It's also we only care when we look at these signals because in these systems the frequency is not different at different points in the circuit. All we care about are the magnitudes of these signals and their phase in relation to each other. So to represent them as such is to write the magnitude here and the phase here, and then we know everything we need to know about the signal. Okay? It's easier to look at this when you start getting used to these phasors than it is to look at 6 cosine of 2 pi times 1k times t minus 15 degrees. Like, that's kind of just overkill. We don't need to know all that. All we need to know are these two things in most cases. Because when we're working on a system, we're going to know the frequency. We don't need to see it in all of our equations and keep writing it. Yeah?
So what does multiplying and dividing these phasors tell us about the signals? Why are we doing it?
Let's say we have a voltage phasor and a current phasor, and we want to do Ohm's law. We can find the resistance phasor.
Okay.
Because V is equal to IR, right? Mm-hmm. Or we have the impedance phasor and the current, and we want to multiply the current times the resistance to get the voltage in the circuit. We need to multiply their phasors because these AC systems don't just have a real impedance. They have a real part and an imaginary part. But I want to get it through everyone's heads that the imaginary mathematicians all over the place really disagree with this term because these things are not imaginary, right? A complex number is a better word for it because it's not imaginary. It's a real number. But now I'm using the word real, which is also used to mean real numbers. Imaginary numbers aren't non-existent. That's what I want to get at, right? And mathematicians typically will say complex numbers, not imaginary numbers. But if I say that this is a real part and a complex part, that's just not correct notationally. So just so you know that these things in the circuit are not imaginary. They're real things, but they're using this mathematical notation to make it easier. Okay? Does that make sense? So when I say that there's an imaginary part of the impedance and a real part, you can't just go, well, if it's imaginary, well, why do I care about it? It's not imaginary. That's just the mathematical notation. Yeah?
When you say imaginary, do you basically mean you can't visualize it in your head?
You can visualize it in your head. It's a real impedance.
It's a real impedance?
But if I say real, now it seems like I'm talking about this.
Right.
It is a existent physical impedance that depends on frequency, and we are only representing it in this manner because now we know that this part of the rectangular complex number is the frequency dependent part, and this part is the non-frequency dependent part. It's literally just to segment it into parts and to keep everything organized. Okay? So if I say that a capacitance has, an imaginary impedance, that doesn't mean it doesn't have impedance. It just means that impedance is frequency dependent. That's all it means. Okay? Any other questions before I go into something more relevant? Yeah.
Do we need to also know how to reverse engineer from that phasor back to?
Oh yeah. Sorry, it's really easy. I was probably gonna get there eventually. If you want to go backwards, you go x is equal to the magnitude. So let me write the magnitude of z times the cosine of the angle, and y is equal to the magnitude of z times the sine of the angle. And then you take that x and that y and put them into x plus jy, and that's it. That's how you do it right there. Your calculator, some people's calculators will be able to do this, and you won't have to do it manually. That's also written in the textbook that I was talking about last time. Let me pull it up. If it takes me more than 1 minute to find it, just cut me off. Okay, let's see what we got. I think it's right in the beginning of chapter 9, sinusoids and phasors. All this stuff's in this book. I can post this book. I think I should post it. So here's what I was talking about, where you talk about the magnitude. They're calling it c, right? It's root a squared plus b squared. So this is the square root of the real part plus the imaginary part. All right? And then the angle is the tan inverse of b over a, which is the opposite over adjacent thing, okay? The b is your imaginary part, and the a is your real part. So that's all in the textbook. See where we get into what I was just talking about. So here they represent the real part with an x and the imaginary part with a y. They say j is equal to root minus 1. And then they say z could also be equal to r angle theta, which is what I'm talking about. This is where the polar comes in. And then this is another way to represent it. Some people's calculators might show it this way. I'm never going to talk about it in this fashion. But if you see something that's r e to the j something, then you know that the r part of that is the magnitude and the j times the angle part is the angle. I'm not going to talk about it in this fashion, though. That's using Euler's formula. Okay, so there's rectangular form, polar form. This is called exponential form, I guess. These are the two that I just talked about. I guess I can't highlight anything. Okay, and here's what I was just saying. So it says, given x and y, we can get r and phi as, here's the magnitude equation and the phase equation. And then on the other hand, if we know r and the angle, we can obtain x and y as r cosine angle, r sine theta. Does that make sense? So if you have the phasor and you get that x and that y, then that becomes your x plus jy, and now you're there. And if you want to go the other way, you use these. So let me just post this book later so that everybody can reference this. Let me write down the page number. Page 377. Okay. Anything else before I move on? All right, so let's move on. This is just an overview. It's all going to be very relevant in the circuits that we're about to solve, but I just wanted to show it as an example, just from the pure standpoint of the imaginary numbers, because this is all we're doing now. We're just translating these exact concepts into circuits. All right? So, let me see what I did last time. I did... Yeah, I started this problem. I'll do this problem again. But I'll actually solve it this time, and it'll probably make way more sense. I always draw the little, I know you can't see what I'm doing right now, but just give me a sec. And I'm going to solve this problem exactly how I would solve your homework problems so that you can follow the same process to solve your homework problems, all right? So let's go 5 cosine 2 pi times 1k times t. And then we'll throw it in Spice and make sure everything's right. Okay? All right, so this is the problem I did last time. Okay, so this is just a simple... See, we're not going to call these really RC circuits anymore because it is an RC circuit, but it's just an AC circuit. When the source is an AC signal, it doesn't really matter what the components are. It's an AC circuit. Okay? So we have a 1 microfarad capacitor, we have a 1K resistor, and basically on your homework I asked you to determine the phasor representation for V in, for V out, and for the current flowing in the circuit. So we have V in, we have V out, and we're going to have an I. Note that the I arrow really does not matter in AC because it's going to be a sine wave, okay, regardless. If it's facing the wrong direction, it's going to be a sine wave that's out of phase by 180 degrees. So what I mean by that is if I drew I this way and my current looked like this, if I flipped one of my components and plotted it in Spice, it's going to look like this. It's going to be exactly 180 degrees out of phase. Like it'll be basically inverted at every point. This looks like DNA now. Now only people who watched will know what I was talking about there. Okay, so let's go. Basically, so I said let's find phasors for V in, V out, and I. So this is the gist of the hard part of your homework. And so we're going to go through this. We have the entire class. We're not doing a quiz today. Let me go look at the assignment again so I can see if I asked anything else. I don't think I did. So I said determine the phasor representation of V in, V out, and I in the circuits. Note that V in is a cosine wave with a phase shift of 0. Okay, so the reason I said that is because you're going to see sine here, and you're going to be, well, what's he talking about? We talked about this last time. In Spice, there's only a sine wave. So if you want it to be a cosine wave, you have to phase shift it by 90 degrees to get a cosine wave. Okay. Both of the inputs are the same. They obviously have different frequencies. This one's 1.5K. This one's 100K. They have different amplitudes. Okay. And I said, note that V in is a cosine wave with a phase shift of 0, which is synonymous with a sine wave with a phase shift of 90. Okay. Verify that your phases are correct by using LT Spice. I say that you can prove that your phase angle is correct by measuring the time delay between signals. Okay, so that's what I'm going to expect you to do on the homework. You're going to calculate a phase of, say, 13 degrees. Well, there's no way to verify that in Spice unless you go measure the time delay between two peaks and then convert that to time delay using the equation that we talked about last time. I'll pull that up real quick just so that I can show these equation right here. So if you go into Spice and you plot your signals, right, for those circuits, you're going to get like a peak for one signal and the lagging signal will come a little later. You measure the time between those two peaks, okay, and then you plug it into this formula right here. You get that delay divided by the period times 360. That gives you your phase, and that should be what you calculated by hand, okay? So that's how you're going to verify that. And we'll go through all this in Spice too today. I'm sure I'll have time. Okay, any questions before I go with this one? All right, so the first easiest thing is to get the phasor for V in. All we need is a magnitude and a phase. What's the magnitude of V in? That's right, so that's 5. And then what's the phase? It's 0. It's 0 because I don't have anything there, so it's basically plus 0, right? So for V in, my phasor is just 5 angle 0 degrees volts. All right? That's my V in. I'm done with V in. Okay? Now to go any further, I'm going to have to convert this circuit into basically phasor domain. so that I can solve it, okay? Because I can't do anything with these values. I need to find the impedances that are associated with these values, okay? We know the capacitors, so the impedance of this capacitor is going to be 1 over J 2 pi F C, right? Or J omega C, this is omega, okay? What's my F here? 1K. What's my C? Okay, so I'm going to plug these in. You don't have to plug in J because it's not going to really make a difference, but let me just plug in 2 pi times 1,000 times 10 to the minus 6. Flip that. I get 159.15. I think that's what I got last time too. Okay. Now, I talked about this last time too. 1 over J is equal to minus J. So I'm going to rewrite this as minus J 159.15 to get rid of fractions. Okay. What's the impedance of my resistor? It's just the resistance. So these are both ohms, okay? So now I have my impedance of my resistor, I have my impedance of my capacitor, I can redraw this circuit. So let's do that. So I'm just going to write this as 5 angle 0. This impedance is minus J 159.15. This impedance is 1K. Another thing you'll see a lot, and I don't know why, I really don't, they won't draw a ground in these circuits. In the textbook, none of the circuits have ground. I couldn't answer that question, so if you have the question for the textbook author, just email him. I don't know why in the world they wouldn't put ground. Because if you try and run this in SPICE without a ground, it literally won't let you.
Maybe because it's an alternating current, technically it would go that way and then it would alternate and go back the other way, so...
It would, but the voltage down here is still 0.
Yeah.
So, I mean...
I don't draw grounds in physics either.
Yeah, I don't know why they do that. Maybe they just assume that you know that the bottom of the battery is ground, so they just neglect to put it there. But just so you know, when you put these in SPICE, you're going to have to use ground. So if we go look at that textbook, let me go find like an example circuit just so you can see what I'm talking about. Yeah, look at all these. None of them have ground. No ground, no ground, no ground. So if you were to put this in SPICE right now and try and run it, it wouldn't work. You have to throw ground there. So when you take 221, if you're going to use SPICE to verify, just so you know, you're never going to be asked again for the remainder of the degree to verify anything in LT SPICE. That's only the way Dr. Baker does things and the way I do them because I think it's very useful. Because when you do these homeworks and you have absolutely no idea what the answer is because you can't find it on Chegg, you use SPICE.
I feel called out.
I used Chegg. Everybody uses Chegg.
Hell yeah.
Chegg is great because if it's used properly, it can be a great tool. You shouldn't use Chegg on exams, but I know people do that too. Not my exams.
Well, your exams are in person.
Exactly.
It'd be very hard to use.
It is. It would be very difficult. All right, so this is V in. This is V out. This is I. Okay, and we're going to solve this exactly how we would solve a normal circuit. Okay? Except we can't use our old tactics because we have this J in there, so we're going to be bouncing back and forth between phasors. But you're going to see that the process is very similar. The math is just more intensive, okay? So even one step further, what I'm going to do, I'm trying to decide. There's a couple of different ways we could do this. We got to either find I first by adding these two in series, okay? They're in series, so we could just add them. Or we could find V out first and then find I. I'm going to go with the find I first because I think that's the way they like to do it in 221. So basically, I'm going to combine those two into one final impedance, which is going to be the sum of the other two impedances. So that impedance, Z total, is basically going to be 1K minus J 159.15. Okay? And so now you see I have a real part and I have an imaginary part. My real part's 1,000. My imaginary part is minus 159.15. And note, when I say the imaginary part, I don't include the j. That's because the j is not part of the imaginary part. The j is telling me that what comes after this is the imaginary part. Okay? So if someone asks you what's the imaginary part, don't say minus j 159.15. It's minus 159.15. Okay? So this is my real.
Isn't notation like
It is.
literally like
It is. It's literally just for notation.
Would it not then be easier to write negative 159.15j?
You could do that too. That's fine. I've seen it both ways. It doesn't make a difference.
why they had to use an imaginary number for like the notation? Like why did they?
They literally did it so that you could use phasors. And because when you use this notation, now we can plot like, because if I just put 1k minus 159.15, that's not right. That would be 800 and, I don't know, what is that, 30.85? Like that wouldn't be correct. They want you to know that this part and this part are two separate parts. And then when you plot them on that plane, you get some magnitude and some phase because they're two separate parts of a vector.
I'm saying they could use like anything.
Yeah, they
could have been,
could have
like,
just
T or
expressed it
T
as a
or,
vector.
I don't know, whatever.
Yeah, they could have just, but then I guess you would assume it's a variable. I don't know. I don't know why they decided to do this. I do know that they talk about how the original way that they did it was just by using vectors. They just did 1k and 159.15 in two different parts of a vector, but the vector math is worse than this math. So they like this better. Because I was reading the book and they talk about how originally they liked vectors better, and then they came across this notation which they found to be easier to use and less verbose, I guess. But just, yeah, so you know, like there's no root negative 1 being multiplied in the physical circuit. It's just a notation thing.
That's what I'm saying. It's like, why even care that J represents I for a complex number, which we're not even going to use?
I don't know.
Maybe it's J.
It's just notation. I could be completely wrong, but this is what I've gathered. I assume it's just notation because I don't see why. I mean, and I've read out there that this just makes the analysis easier. There's no physical meaning of this J.
Right.
Okay? So just bear with me. I'm helping you for 221.
I think sometimes you multiply j and j together, like when you distribute, and then it becomes negative 1.
It does, yeah.
Flip the sign.
That's true. So yeah, in those cases it will have some relevance. I don't know what the physical relevance is there, but yeah, when we do frequency response, I probably won't get there this semester. We're almost out of time. But frequency response is basically, instead of looking at how a signal behaves over time, we look at how a signal behaves over frequency. Like we're looking at, well, how does this signal behave if the frequency is 1 hertz all the way out to how does it behave at like 100 gigahertz? And you get this plot that's called frequency response. And when you're doing those, a lot of times you will like square things to find the magnitude, and the j will get squared, and you'll end up with a negative 1. So that probably has some relevance. I don't know. Right now you don't have to worry about it. You will in 221. All right, so we've got Vn, which we know to be 5 angle 0, right? And we've got this complex number for my z, and I know, based on Ohm's law, that I is equal to V over R, right? So basically, if I can get this ZT in terms of a phasor, then I can go 5 angle 0 over my impedance. I guess you could, in this case, it would be V over Z, because this is impedance. So for AC, it's not V equals IR, it's V equals IZ, but it's just resistance. It doesn't really matter. We basically need to find a phasor for this impedance so that we can divide the two phasors and we can get our current phasor, okay? So let's get a phasor for this. What did I say? I said that the magnitude is equal to the square root of the real part squared plus the imaginary part squared, right? So this is going to be 1k squared plus 159.15 squared. Note that the negative doesn't matter when we find the magnitude, because if I square a negative, I still get a positive. So I'm not writing the negative 159 because it doesn't matter. You could. It's going to square and it's going to go away. Okay, so let me throw this in my calculator and let's see what we get for the impedance. 1000 squared plus 159 squared. Oh, let me put the 1.15. And then I square root. So I get a magnitude of 1.013 K. And now I need an angle, and that's going to be my phi is equal to tan inverse of, I said it's the imaginary part over the real part. Now the negative does matter. Note that the negative matters always, but when I square it, it goes away. I don't want you to think that I'm saying it doesn't matter here. It does, but it's going away when I square it. Okay, so that's my phase angle. Let's plug that in. Tan inverse of negative 159.15 divided by 1,000, negative 9.04. And that's ohms. So that's Z in phasor form. All right? Now, I have my voltage in phasor form, I have my impedance in phasor form, and now what I need to do is I need to go voltage divided by impedance, and I can get my current, okay? I'm kind of running out of room here, but I think I could just do it right here. So it's going to be 5 angle 0 divided by 1.013 K angle negative 9.04 degrees. Okay? And I talked about it, but let's go and look at the textbook, what the textbook has to say about it. Basically, when I divide two phasors, all I do is divide their magnitudes and I subtract their phases. So it's really easy math, like you don't need to do anything crazy. But let's go make sure that the textbook agrees with me. You mentioned that last time. I don't know what they're talking about.
She's so tall.
Alright, that's too much reading. Alright, let's see.
I don't think it actually said a word about the segment.
Yeah, it didn't. It didn't even mention it.
She's just flexing.
Oh, okay, so it's right here. So it's showing that if I... Here, addition and subtraction of complex numbers are better performed in rectangular form. Multiplication and division are better done in polar form. Polar form is phasor form. Okay, so those are going to be used interchangeably. I'm going to say phasor, they might say polar, it's the same thing. But, so you see here, if I take two complex numbers and add them, you add their real parts, you add their imaginary parts. That's exactly what I was talking about. If you want to do subtraction, it's the same thing. Okay? You subtract their imaginary parts and their real parts. Okay? Multiplication, you just multiply their two magnitudes and you add their two phases. Okay? Division, you divide their magnitudes and you subtract their phases. Okay? So this, here, let me write this again. What page is this? Oh, it's also 377, so I already wrote that on the other one. So this is all really useful stuff. But we're basically looking at division, so we're going to divide them and then subtract their phases. Okay? So if I divide 5 divided by 1.013 K, I get 4.93 milli. Okay. Angle 0 minus negative 9.04 is just going to be negative or positive 9.04.
Isn't it minus negative 9.0? Oh, okay.
Yeah, so it's going to be positive, and that's going to be amps. So you could put the milli out there too if you want. I put it here, but you could write basically 4.93 angle 9.04 milliamps for I, and that would be perfectly acceptable. Okay, so I got my I, right? Let's go check in Spice if that I is correct. Any questions before I go to Spice? Yeah.
So going back to like 5 close 9, 2, 5, 18.
Where is that?
Top left, yeah. Spice you do that and then just sign them in plus 9.
Yeah, you have to basically, that was the point of the last homework, was to get you to look at this and then know how to put that in Spice, because in the textbook, they don't give you anything in terms of what you're going to see on Spice. So you have to just look at a circuit and know, okay, I know what I need to put into Spice. like right here, they put 10 cosine of 4t. If you don't know how to put that in Spice, it would be amplitude of 10, a sine wave with a phase of 90, right, because it's a cosine wave, and then the 4 is my 2 pi f. So if you want to find the frequency, you have to divide 4 by 2 pi. So this is like an unrealistically small frequency, right? It'd be 4 over 2 pi, which is like less than 1 hertz. Like, that's unrealistic. But they love to use unrealistic values in this textbook. Like 5 ohms and 0.1 farad, that's never going to happen in a circuit. They just like to use these values. I don't know why. It makes the math easier, so you don't have to do all the unit conversion, but it's not practical, okay? So I use microfarads, nanofarads, picofarads. Those are real values of capacitors. You're never going to find a 0.1 farad capacitor. It's just not, they're not out there. And if they are, they're used in power systems, and they're definitely not used in series with a 5 ohm resistor, okay?
A lot of our physics problems are like that. They're like 2 and 3 ohm resistors that we have to.
Two Henry inductors. You know, that's like the Earth's inductance. Like, that's unbelievably unrealistic. Like, it's just not even.
We just connected the Earth in a circuit, man.
Oh, I answered your question?
It's in series with the sun.
All right, let's build this. So I got a capacitor, resistor, this is 1K, this is 1 micro, this is the out, sine, do you guys like LT Spice now?
Yeah.
Yeah. That's good. Okay, so I've got my cosine input. Everybody sees I did sine. I've got 5 amplitude, frequency of 1K, phase of 90. That gives me the cosine basically of 2 pi 1K t. It's the same thing, okay? Now, let me go run a dot tran of like, I don't know, 6 milliseconds. Oh, it's something else you should do, and you're going to start to see if you want. Let me just show you what happens if I run this. You'll see this like kind of strange startup. You see that weird looking startup? So what you want to do is maybe, instead of running a dot tran by typing it, what you can do is you can come up here and hit run, and when you do the transient, you can put the stop sign at like 10 milliseconds and time to start saving 5 milliseconds. It'll skip that initial startup. It's basically getting the capacitor charged to where it'll operate most of the time, but that startup is because of the initial conditions and whatnot. So if I run it now, we won't see any weird behavior like that, right? Okay, so that's my output. We're going to get there. And there's my current. Something seems wrong. Did I use the right values?
No, I thought I got a mistake. You're good.
Did I make a mistake?
I think you're right.
I want to see if this peak is... Yeah, perfect. Okay, so you see that I'm at the peak of the current, and its amplitude is 4.923 milliamps. I calculated, what did I calculate, 4.93 or something? So that's correct. And so now what we'd have to do is go and determine, did I get 9.04 degrees phase shift right? Well, let's calculate over here what the time delay should be, and then we'll see if that time delay matches Spice. It won't be exact, but it should be pretty close. This is where you're getting into like more, you're going to be moving the cursor to where you think the peak is, and it's going to be slightly off. So if you're within... you should be close. I mean, if it's 2 milliseconds and you get 4 milliseconds, you're wrong. Like, but if it's 2 and you get 2.2, then it might be right. Like, don't kill yourself over that. All right, so basically we take phase, we divide it by 360, and we multiply by the period to get my time delay. Okay, so in this case it's going to be 9.04 over 360. My period for a 1 kilohertz is 1 millisecond. Okay, so what you notice is I'm just multiplying by a fraction of a millisecond, right, to figure out what fraction of the period am I off by. So 9.04 divided by 360, and I multiply that by 0.001, I get 25.1 microseconds. Let me write that.
Where'd you get 1 millisecond from?
That's the period of my frequency. That's 1 over my 1K gives me 1 millisecond. So this is 25.1 microseconds. Okay, so that's what I should see in SPICE to confirm that this phase shift is correct. All right, let's go. Oh, that's not SPICE. Let's go to SPICE. So what I'm doing is I'm looking at the peaks of these two signals, and I want to see my VN and my current are what I'm looking at, the difference between the two. Let me go remove this cursor. We'll zoom in on one peak, okay? And I'm going to play. So another thing that's annoying about LT Spice, if you can figure it out, please tell me. I don't think you can put cursors on two different signals. But what you can do is you can put two cursors on the same signal and line them up where you want them anyways. But you can't like put one on the blue signal, one on the black signal. I don't think. So let me do. I'll just put them both on the blue signal, and you'll see I can move this one still to the peak of the black signal, but it's not on the black signal. As far as time goes, it's in the same position as that would be. Okay, and then this one's at the peak. So I got 23.6 microseconds. I calculated 25 microseconds. See, that's close enough. That is close enough. If it was like 15 microseconds, that's not close enough. You did something wrong. But if it's within the ballpark of a couple of microseconds or whatever unit you're looking at, then it's good enough. Oh, we're looking at the difference between the two peaks because that's the phase shift. It's basically how far the signals are not overlapping. They're slightly shifted from one another, and we're looking at the difference. So this horizontal, you see this horizontal? It's the difference between my cursor 2 and my cursor 1. So I put one cursor at the peak of the black signal and one cursor at the peak of the blue signal. You can't really tell though. So
How much they're lagging or leading?
yeah. So in this case, my current occurs slightly earlier in time than does my voltage, which means my current is leading my voltage. Okay?
Which is normal.
Huh?
How'd you get that box signal first?
Oh, okay. So if you click on a signal once, it gives you one cursor, and that box just pops up, and then you click on it again, and it gives you the second cursor, and they're both there. It's just really annoying and hard to see.
Okay.
You see it? You see me moving it, right?
Yeah.
You see it down here now?
Yeah.
It might be easier if I remove the grid. Let me shut the grid off. Oh yeah. Okay, so here. So I move this. You can get as close as you want to these peaks, and then you just put them at the peak. So I'm assuming that that's the first peak right there, right? I'm assuming that that's where the peak is. I'm just putting that there. And then, like I said, I can't put another trace on the blue one. They're both on the black one. So I'm just going to try and move it horizontally to where I think the peak is. And I might say it's like right here. And then it gives me, okay, so I calculated 27 microseconds. I still calculated 25. It's close enough.
Have you tried getting two block peaks and then putting one up there and then another one?
Yeah, I'm pretty sure what will happen is it'll only let me operate in one plane at a time. Oh, maybe you're right.
Because I'm pretty sure that's what I do.
Hang on. Well,
And then move the other one.
oh, nice. There you go. Okay, so let's put that there, and that there. Really? I must have gone too far. I can't tell where the peak is. That's what's annoying. I mean, it's close enough, right? This is 25 microseconds. So yeah, okay. So if you split the plot planes, I guess that works. Thanks. Everybody understand why this confirms that my calculation is right? I basically converted the delay in degrees or radians to a delay in time, and then SPICE can measure that delay in time to prove that I got the correct phase. Okay?
Do we need to show that from Spikes? I don't know where to like a screenshot of that.
Yeah, and what you can do is you can just right click once you get the cursor where you want it. Well, you don't really have to do all of this, but you can if you want for yourself. You go draw cursor position, and it'll plot a little arrow that tells you the time stamp and the current. That's something you could do. Or you could just take a picture of this box and like highlight the the time delay that you got. But definitely show that the cursors are on the peaks, because if you just move them to some random position and just show the box, Abraham's not going to believe that you did it. So make sure you get like a little snip showing that your two cursors are on the peaks and then this next to it or something. That's good? All right, so we found V in's phasor. Okay, now we need to find V out's phasor. Okay, and it's really easy because all we have to do is I over R again, but for just across the output. It's the same. It's just using Ohm's law again. So let's go back to the paper. So let me get another piece of paper. All right. So I've got so far. Let me just leave this here. Let me keep consistent. I've got V in is equal to 5 angle 0. I've got I is equal to 4.93 angle 9.04 milliamps. And now I want to find V out. All right. And so, let me draw the circuit again. I know my I. And I know my Z. Okay, so I'm trying to find this voltage, right? The voltage across the load, because that's my V out. So if we were doing Ohm's law, all we would do is multiply, right, my current times my resistance. Okay? So that's literally all I'm going to do, is I'm going to multiply my current times my impedance in this case. So V out is equal to I times Z, which is equal to 4.93 angle 9.04 times my impedance is 1K. Okay, so in terms of a complex number in rectangular, that'd be the equivalent of 1K plus J0 or 0J, right? So if I want to find the magnitude, it'd be the square root of 1K squared plus 0 squared, which is just 1K, right? So that's going to be my magnitude. Okay? And then my phase is going to be the tan inverse of 0 over 1K, which I think should give me 0. Yes. So I have basically a phasor which is Z is equal to 1 kilo ohm angle 0. All right? Multiply this by 1K angle 0 ohms. And like I said, when I want to multiply two phasors, all I do is multiply their magnitude and I add their phases, okay? So V out is going to be 4.93. I have a milli and I have a K. The milli and the K go away, so I just get 4.93 volts basically. And I add their phases, angle 9.04 degrees. That's V out. All right? So now if I go back into Spice, I should be able to see I have the exact same phase, which means my current and my V out should be right on top of each other, right? They're both shifted from the input by 9.04 degrees. So let me tile these vertically and get rid of this. Zoom out. And then watch what happens when I plot V out. You can't even see it on this plot because it's exactly the same phase shift as my other signal. So let me put them all on the same plot. Actually, let me put it on 3 different plots. I've got V in, I got my current, and I've got V out. Well, let's go look at the peak of V out. It should be 4.93 because that's what we calculated. And you see right here it says 4.92 volts, right? So that means I've got V out correct. All right, so that's that one. Does anybody have any questions about anything I did in Spice or on the paper? Yeah.
ALT splice, where are there 3 ways instead of 3?
V in, V out, current.
Uh, do we actually need to be in, James?
I put it, I mean, you don't need to plot it. I mean, I put it on the homework asking you to find the phase so that you get used to going from this to a phasor because you need it to solve the problem. You can't solve the problem without knowing the phasor form of V in, so I might as well ask you for it.
Right.
You can't do voltage dividers on this stuff.
You can. You can. Would you like me to solve this exact same problem using a voltage divider?
Yeah.
All right.
Because I was wondering, like,
It will work exactly the same. All right. So should I go to a different piece of paper? Let me try a different piece of paper. All right. All right. So if I want to do a voltage divider, it would basically be right, that would be my 2 impedances. I would treat them like 2 resistances, right? And so I would go V out basically equal to 5 angle 0. Z2, we just did it, right? It was 1K angle 0, right? And now I'm going to have to find the phasor of them added, which I already found, right? Z total, that was what we did earlier. That was, let me bring that up. 1.013K angle negative 9.04. All right. So I'd first divide here, right? I would go 1K divided by 1.013K is going to give me that probably that 0.493 or that 4.93. Or sorry, no, it's not. That's after I multiply by 5. 0.987. And then my angle is I subtract them, right? So it'd be 0 minus negative 9.04 would be 9.04. Now I can multiply these two phasors. 5 times 0.987 gives me that 4.93. And then my angle as I add them, 9.04. So does that make sense to everybody? That's exactly. You need to keep track of the forms, okay? Because if I throw one of these in there in rectangular form and one of them in there in phasor form, nothing's going to work. You're going to be like, well, how the hell do I do this math? The phasors should be divided and multiplied, and the complex number should be added and subtracted. Notice I didn't turn 1K into a phasor and minus J159.15 into a phasor and then add them. I just added them because it's so easy to add them. You just add the real part to the imaginary part and you get a new number, okay? That's how we got, but then we went and found the phasor for that complex number, okay? So there's going to be a lot here. It's going to be challenging because you're not used to doing this and there's a lot going on, but you see it's just the same stuff. We're using Ohm's law, we're using KVL, we're using voltage dividers. Everything's just a little bit more complicated because our signal input is more complicated, right? Any questions about this or the last problem?
What is the formula for the impedance of an inductor? It has nothing to do with either this or the last problem.
So the impedance of resistors are the impedance of a capacitor is 1 over j omega c. The impedance of an inductor is j omega L. All right, and omega is equal to 2 pi f. I think I talked about that last time, but
Yeah, you mentioned.
yeah. So on the homework, when you go to do this other problem, let's go back to it. You're going to see an inductor, and so you'll go through this same process, right? Except this inductor's impedance is going to be J times 2 pi times 100K times 10 millihenries, and then that'll be your value, all right? It's the same stuff. Does anybody have any questions about the process? Because you can do a voltage divider here too. It's the same thing. These are just impedances now. That's why this is so much easier than the RC and RL part of this, because this can just be treated as an impedance. This can just be treated as an impedance. That's a voltage divider every time. Yeah.
So I was saying, like, the last time we were using DC, that they're similar to, like, resistances. That was incorrect. In this case, they're just technically all impedances.
They are all impedances, which are technically resistances, but they change according to the frequency in the circuit.
Okay, cool.
They resist change in current or voltage depending on the frequency. That resistance changes depending on what the frequency is, and that's why their impedances have F as a variable in the value, right?
Yeah, makes sense.
Any other questions? Yep.
Why then?
That's just the properties of these components. If I had to take a guess, it has to do with the time that it takes to charge a capacitor, the time that it takes to energize an inductor. If you're pushing energy in and pulling it out really slowly versus pushing it in, pulling it out really quickly, the device, whether it be a capacitor or an inductor, has more time to charge or energize or discharge and de-energize, which would make it act like a bigger or smaller resistance for the flow of the current in the circuit. It makes sense to me that it depends on the speed, because these devices have to take some time to charge and discharge. So if you have a much larger capacitor, it takes a lot longer time to charge. And if you put a larger capacitance here, that would also give me a smaller impedance. It's not really resisting the flow because nothing's going in and nothing's going out. It's not charging or discharging at all. It's basically going to act like a short. But yeah, it's too complicated for me to know for sure. It's not too complicated for someone to know for sure, but it's too complicated for me. I'm sure Dr. Baker could answer that. Yeah, he can. Any other questions? Any recommendations for what I should do with the remaining 12 minutes? Does anybody want extra help? Or do you want to leave? Yeah, I think I'll probably put one. I mean, it's useful stuff. This is going to get you through the first whole segment of, here, check this out. So 221 covers chapters 9, 10, 11, 12, 13, 14, 15 of that book, I think. Well, they skip over some of those chapters. It's not all that crap. No, it's probably 9 through 15, actually. However, we've just basically covered everything you need to know for chapters 9 and 10. So that's like the first quarter of the class. So if you go into the book and you look at the chapters, this whole sinusoids and phasors I covered in the first 15 minutes today. I don't think you need to know anything more on those. And sinusoidal steady state analysis is what we just did. This is called steady state analysis. All we have is a sine wave. Nothing's changing in the circuit other than the input, so everything else acts accordingly. AC power analysis you'll go over. That's just power equations, calculating power dissipated, apparent power, real power. That stuff's just a bunch of equations. I don't know that you'll do a lot with chapter 12, but you might. That's three-phase power. I talked about it really briefly, how Three-phase power is basically you have one signal at 0 degree phase. One of them's out of phase by 120. The other one's out of phase by 240. That's how power is transmitted everywhere. There's a reason for that. It maximizes the amount of power. Yeah, I asked because if you use 4-phase, 5-phase, 6-phase, you're still increasing the power delivered with each phase that you add, because the average power of those three signals increases because I don't know. I did it once on LT Spice and I proved it to myself. But the reason why they don't use like 4 or 5 or 6 phases is because they're also trying to limit the number of wires that we need running through the city. So they figured out that if we just use 3-phase, we can use three cables and we can maximize the power and minimize the cost of material, basically. Magnetically coupled circuits, those are going to be inductors. You'll see they'll start talking about the magnetic field around and through an inductor. You'll talk about how they're coupled, because this current flowing through this one induces a magnetic field on this one, which induces a current on that one, which induces blah, blah, blah. All the crap about how they fight over whose magnetic field and whose current is inducing what. Those are transformers. I know in here you talk about transformers. A transformer is basically just 2 coils back to back. And then, like I said, you'll talk about frequency response, which is basically talking about how circuits respond to different frequencies. And this is basically everything you learn in 221. Yep.
Is this week or next week the last week to make the quiz?
Yeah, I'm going to make the last day a week from today, April 27th. Let me write it on here so that if anybody doesn't watch my lecture but looks at the notes, they have no excuse. All right. Nothing else? Yes.
There's a list on Wikipedia of inventors killed by their own inventions, and the creator of the Segway is on that list.
Are you serious?
Yeah, the creator of the Segway died by Segway.
Wow.
He segued off a cliff. He was trying to prove the stopping power of a Segway, and he segued off
And he
a cliff.
failed.
Yep.
That's horrible.
I mentioned that last time we talked about segways.
I didn't even hear
Died
it.
on the segway.
That's terrible. What was your question?
Is the final the whole semester or just after exam?
The whole semester.
Let's go.
Come on, the DC stuff's easy.
Yeah.
Isn't it easier than this?
Yeah. Are you going to make us do Thevenin and Norton on the final?
Probably. You have 2 hours. I got to make you do everything.
You really gonna put one of these on?
For real. You're going to spend the next 5 days doing this homework, or you're going to spend the last day doing it, which you're supposed to be spending the next 5 days doing it.
Do an hour a day.